Hello everyone. So we'll be discussing a topic called double titration, right? So this is a JEE advanced topic. Maybe you can expect lighter version of this or lighter version questions in JEE main, but basically this is a JEE advanced topic, and this particular video that I'm making, it's mainly for students who are revising, right? Because we will be discussing few things from the ionic equilibrium. We'll not be going into the depth of that, but we'll be discussing those topics as it is understood to you, right? It is you already, as if you already know that, right? But I'll try to keep the explanation to very simple and minimal exposition or jargons related with ionic equilibrium, right? So that this will be useful for the students who are learning this for the first time and those who are in the 11th who hasn't still done equilibrium. Okay, so without wasting much time, what is double titration, right? The term is right, the double. So what double titration is basically titration. I'm assuming that you already know very well about the titration, both redox and the acid-base titration very well until now. So titration using two indicators, double, right? Two indicators, right? Two indicators and titration of. So we will discuss this double titration. Double titration is a big topic. It's a big topic, but we will discuss the part of double titration, or we'll discuss the very basics, but we'll focus on to the double titration part, which is which you may find as questions in your entrance exams or practice sessions. So titration of mixture of salts, right? So mainly Na2CO3 and NaHCO3. Okay. Sometimes we will add NaOH into it, but that is something we already know, right? Strong acid and strong base, right? Now the titration is done against, titration can be done against anything, but titration is done against, titration is done against strong acid, right? Such as HCl or H2SO4, right? Because otherwise this thing will become more complicated, right? Uh, you can try with the weak acid. So if you find any difficulties in that, we will discuss it, right? So we'll discuss with the strong acid because even the PYQs on J Advanced or practice questions that we can find from very good books, it only covers with the strong acid. Okay. So before going into the double titration, right? What is double titration? So let's talk about these two indicators. These two indicators that we are going to use are phenolphthalein and methyl orange, right? Okay. So let's see these indicators, how do they work? So indicator and let's say color transition range, right? Indicator and color transition range. So what happens is, what is the meaning of color transition changes? When does the color change occur? Because that's when you can find the equivalence point, correct? Color transition range. So suppose the indicator is phenolphthalein, right? Phenolphthalein, this which you can write as HPH, right? Sometimes we just write pH also, but pH might go for the phenyl group. Anyway, the color transition range, writing it in pH, right? So this is from 8.3 to 10. Okay, 8.3 to 10. So the color of phenolphthalein changed from colorless to base in the range of 8.3 to 10. Basic. Okay, clear? So even the 11th students who are into 11th, they already use phenolphthalein in acid-base titration. And you already know about phenolphthalein and methyl orange. How does the color change in basic and acidic solution? You just didn't know about the pH change maybe. Some students in some syllabus might have learned about the pH range as well. Anyhow, methyl orange, right? Another very common indicator, we can represent it as Me. Okay. So this shows the color change from 3.2 to 4 point. So kind of a very weak weak acidic range. Okay. So keep this in mind. Phenolphthalein range is 8.3 to 10. Methyl orange range is 3.2 to 4 point. Okay. Now, now, how do you find which indicator is suitable for a particular titration, right? So I'll give you a point. This will, for 11 students, we'll again discuss this in equilibrium chapter. For 12 students, you already know, so I'm just revising it. The mid value of CTR of suitable indicator should be almost near the equivalence point. So you already know what is equivalence point. Equivalence point is when we get equivalence, concept of equivalence, right? Whatever we are titrating. So the pH at the equivalence point, that should be almost equal to the mid value of CTR. If it is exactly equal, it's a perfect indicator. But if that value comes in the range or near to the mid value of the indicator, that is really good. Okay. So keep this in mind and we will use this. Okay. Now, uh, okay. So mid value of pH. So we'll write it as pH again. Okay. Clear? We'll use this information. Now, as we were talking about Na2CO3 and NaHCO3. So both are, you see, Na2CO3 and NaHCO3 are salts of NaOH and H2CO3, right? H2CO3 is a weak base, sorry, weak acid, correct? NaOH is a strong base, right? Let this be there. Anyway, so let's see what happens here. So we need to understand how does H2CO3 act as an acid. Okay. So let's see. Let's talk about H2CO3. Okay. So H2CO3 is a weak dibasic acid. You already know what is basicity, right? We learned in 10th class, both IGSE and CBSE students. So H2CO3, right? What happens is it becomes H plus. Since it's a weak acid, we'll write an equilibrium. H plus plus HCO3 minus, and this will be Ka1, right? Then you have H plus plus, uh, sorry, CO3 2 minus. Okay, so this is Ka2. And the values of Ka1 and Ka2 are, since it's a very weak acid, you have Ka1 is equal to 10 raised to minus 7 and Ka2 is equal to 10 raised to minus 11. Okay, just keep this in mind because we will have to use this. Okay, cool. I'll go to next page. You can take the screenshot or you can write. So let's see Na2CO3, right? So first titration, Na2CO3 titration against HCl. Okay. Suppose we are dropping HCl into a flask which contains Na2CO3. Okay. So what will happen? Na2CO3, well, Na2CO3 will create, we will have Na plus, 2Na plus CO3 2 minus. Okay. So this CO3 2 minus will react with HCl, right? And we will get HCO3 minus plus Cl minus. So the Cl minus and Na plus, that will be the NaCl, correct? Okay. So yeah, you can mark the aqueous for everything, but let's leave that anyway, it's understood, right? So this is a amphiprotic acid. It's weak acid, but amphiprotic acid. What does it mean is it can take an H plus and become H2CO3. Also, it can release an H plus and become CO3 2 minus. So how do you calculate the pH of amphiprotic acid? So this is a part where I said it will be easy for the students who learn, for the 12th students or revising students, because this pH calculation is coming from the ionic equilibrium. But don't worry, just understand pH of this will be, right? pH of this will be pKa1 plus pKa2 divided by 2. Now P meaning, so pKa1 is actually minus log to the base 10 Ka1. Okay. So we have the values here, 10 raised to minus 7 and 10 raised to minus 11. So you will get 7 plus 11 by 2. How much is that? You will get around 9, right? And you will find that this value, right? This is a pH. So which indicator will be suitable for it? Let's see. You have 8.3 to 10. So if you add it, you get 16.3, right? So you'll get around, sorry, you will get 18.3. So you'll get around 9.15, right? The mid value. So 9 is almost equal to 9.15. So which meaning phenolphthalein phenolphthalein is the suitable indicator, right? So you keep this in mind. Phenolphthalein is a suitable indicator. Methyl orange is not the suitable region because its mid value is not coming in close to 9. It will come 3.2 and 4.2, so almost 3.5, 3.6, that range. Okay, so phenolphthalein is a suitable indicator to find Na2CO3 titration against HCl. Okay, this is clear. Okay, very good. Now, if you go Na2CO3, so phenolphthalein is the best indicator. Now, if you check for its second equivalence point, okay, so let's see second NaHCO3 against HCl. You need to understand here we are creating HCO3 minus, right? So that will also get converted as NaHCO3 minus, correct? So let's look at this. HCO3 minus reacting with HCl will give you CO3 2 minus, wait, sorry. CO3 minus reacting with HCl will give you H2CO3 plus Cl minus. So NaCl, then H2CO3, right? Hydrolysis. Uh, we have a salt, then it's reacting with acid. So you get H2CO3 plus Cl minus, right? Now, you see H2CO3 is a, as I said, weak dibasic acid. What will be the pH of it? pH will be half of pKa1, right? pKa1 minus log C, right? C is basically concentration. So those students who haven't learned ionic equilibrium but learning this in the 11th year, learning this redox before ionic equilibrium, just keep it in mind. This is just a formula which you will learn in ionic equilibrium. So log C we don't have the value, right? But pKa1 we have the value which is 7, right? Log C concentration anyway will not take very high. So if it is 0.1, then it will be 1. So minus 1, then 7 plus 1, 8. So it will come around 4. So this will, pH of this range will come around 4 to 5. Correct? 4 to 5 or little bit, very close to 4.5 that range, or 4.3, 4 to 5. So let's suppose we have 4, right? So which this methyl orange you have 4.4 plus 3.2, right? So you get 7.6, 3.8. So very close to this pH. Okay. So as I said, this pH range can vary from log C, but more or less it will be close to 4. So methyl, sorry, methyl orange is the suitable indicator, right? And you need to understand, see, this is the first equivalence point. What do you mean by first equivalence point, right? So you see, solution was basic and we are adding acid. So the pH is decreasing. And this is what will happen first. Na2CO3 will get converted into HCO3 minus, so NaHCO3 then, right? So this is the first equivalence point. That meaning this is the phenolphthalein will show the color change around this pH, right? This is the first equivalence point. So now let's suppose we already had NaHCO3 and Na2CO3 getting neutralized by HCl, that also created HCO3 minus, right? And here you have NaHCO3 from the Na2CO3, and if we had NaHCO3 already, then that. But this is the second equivalence point where the methyl orange will change, show color change. Okay, second equivalence. Okay, clear? Now, so you have this. So this is second equivalence point. Now you need to understand. So we take an assumption that, let's say, one case, if you only used, right, uh, Na2CO3 versus HCl, versus meaning titration, and only using, I'll just write HPH as indicator, right? So you're only using phenolphthalein as the indicator, only phenolphthalein. So what will happen? First, Na2CO3, HCl will give you NaHCO3 plus, what will you get? NaHCO3 plus, okay, yeah, you get NaCl, correct? Get NaCl. So NaCl will be the, now, so this is, what do you have? You have phenolphthalein. So this is the first equivalence. And how do you understand where is the first equivalence point? Phenolphthalein solution will change color from, how will it change? Color from, how will the color change will happen, right? So it is becoming base to kind of neutralize. So it will change from pink to colorless. So I'll write it here. change color. I'll show the color change. Pink to colorless. I'm giving this because in some questions I've seen, instead of saying it's the equivalence point, they're just saying about the color changes. Okay, so it's the first equivalence point. The second thing that can happen is NaHCO3 reacting with HCl, what is left. So you need to understand this NaHCO3 is created from the Na2CO3, right? We have HPH, right? Because that's there in the solution. We get H2CO3 plus NaCl again, correct? This is the, let's say this is a second equivalence point, right? See, whenever this equation reaction happens, the equivalents are same, second equivalence point will reach. But will we detect it using phenolphthalein? No, because as we found out, this pH range, uh, phenolphthalein is not the suitable range indicator, right? So, you can write can't be detected by phenolphthalein. Okay, keep this in mind. First, equivalence point will be detected by phenolphthalein. Second, will not be detected by phenolphthalein. Okay. Now, let's look at the second case. We have NaHCO3 versus HCl. Correct? We have NaHCO3 versus HCl. Right? Uh, wait, not NaHCO3. Sorry, both it's same Na2CO3. Again, Na2CO3 versus HCl. But only methyl orange is used indicate. Okay, so only methyl orange is used as indicator. So you have again Na2CO3 plus HCl. You get NaHCO3 plus NaCl. Correct. So this is the first. Just writing EP equivalence point. Now you see, you know the range of pH, equivalence point range, which is coming as 9, sorry, 9.5, 9.23, 9.15. And the MEOH range is not in that. So can't be detected, right? Can't be detected by MEOH because the range, color transition range and the equivalence point range is not coinciding. So we will not get the color change. Okay. Now let's see next second equivalence point. You get MEOH. You have H2CO3 plus NaCl. Right. So this is the second equivalence point. Now here color change happens. So detect, you can write detected by MEH. And why is that? How can we see the color? How can we see this is a second point detected by MEOH, right? How color change from yellow to red. Okay, so you can see that. Okay, second equation. So using MEOH, only MEOH, you cannot find the first equivalence point, but you can find the second equivalence. Using only phenolphthalein, you can find the first, but not the second. Okay, cool. Now, I'll give you a small table to do the question. It's just like a trick. Let's say compound and sorry. So compound, then phenolphthalein, then methyl orange. Okay. So the compound, this is a compound which will be titrated against HCl or any strong acid for that case. Let's take HCl. So first one, it is NaOH, very strong base, What is the N factor of it? 1. And HPH, see, if you titrate with HCl, it will 100%, and the equivalence point that you will see with HPH will correspond to the 100% neutralization of what? NaOH. Even MEOH will also give. Because strong acid, strong base titration, you can use any indicator. Okay, you can use any indicator. Second, you see, if we use, let's say Na2CO3. Na2CO3 is, N factor is 2, right? Already know that. We learned it in equivalence. HPH, let's suppose Na2CO3, when it gets converted into NHCO3, right? It doesn't the full neutralization hasn't happened. Let's suppose that is 50%, right? But when we are finding out the second equivalence point with MEOH, it is 100%, correct? So third, you have NaHCO3, in factor is 1 again, right? So HPH, it will no reaction. I mean, if you use HPH, you will not find the neutralization point or equivalence point of NaHCO3. But with MEOH, you'll find the 100%. Okay, so read about this. Okay, keep this in mind. This is very important. So NaOH, you can use both. Na2CO3, you'll get the 50% mark at HO using phenolphthalein, and 100% one with methyl orange. NaHCO3, if you use phenolphthalein, you will not get the point. Okay, but if you use methyl orange, you will get the final one, 100%. Okay, so yeah, so this is what we are going to use. So I'll show a question, I'll solve a question, so it will be very clear to you. Then using that understanding, you can solve more questions from better books or anything. Okay, so the question, 50 milliliter, 50 milliliter of a solution, 50 milliliter of a solution. Okay, so you have 50 milliliter of a solution containing 0.01 moles each of NaOH, Na2CO3, and NaHCO3. So sodium hydroxide, sodium carbonate, and sodium bicarbonate. Okay. Then was titrated against normal HCl, which meaning one normal HCl. Okay, right? What will be the titer readings if, so we have 3 cases. You need to find out the titer reading on all of those cases. First case, only phenolphthalein is used as the indicator. Second case, only methyl orange is used as the indicator. Third case, very important, very interesting case, MEOH is used, right? Sorry, not used. MEOH is added. MEOH is added after first equivalence point with phenolphthalein. So do you understand the question? You have a solution, 50 milliliter of solution containing 0.01 moles of each of NaOH, Na2CO3, NaHCO3. Then we titrate it against one normal HCl. So we have to find out the titer readings. If first case, only phenolphthalein is used as indicator. Okay. Second case, only methyl orange is used as indicator. Third case, We use the phenolphthalein first, and you get the first equivalence point. Then you add methyl orange, and then you titrate. Okay, so they're asking how much of volume was required after adding the MEOH. Okay, cool. So you can pause the video and try the question, right? Anyway, I hope you have done that. Now let me show you how to do this question. Okay, so the first case, right? Only phenolphthalein was used. Okay, only phenolphthalein was used. So let's see, we have a solution where NaOH plus Na2CO3 plus NaHCO3, right? Reacting with HCl, right? Presence of HBH. So see, using phenolphthalein, we can only find first equivalence point, correct? So this will be 100% used, this will be 50% used, and this will not be used, right? This will not be the phenolphthalein that at that equivalence point that we find by phenolphthalein, right? We will not have used any, I mean, HCl wouldn't have neutralized any NaHCl. Okay, so these. So let's write the concept of equivalence. So I can write equivalence of NaOH plus half of equivalence of Na2CO3 should be equal to equivalence of HCl, correct? Equivalence should be equal. So equivalence of NaOH is, well, it's already given. How much is that? 0.01 plus, then you have half multiplied by number of moles. So here the n factor is 1. So anyway, doesn't matter. Here the n factor is 2. So 0.01 equal to equivalence of HCl is, it's given, you don't know the volume. So you take the volume, right? Multiplied by 1 normal, right? So 1. So what is V? V will come out to be how much? 0.02 liter, which is 20 milliliter. Okay. So the title reading for the first case is 20 milliliter of HCl. 20 milliliter of HCl. Okay. I hope this is clear to everyone. Now let's go to the second one. Only MEOH is used, right? So you have the solution again, NaOH plus Na2CO3 plus NaHCO3, correct? Have HCl, you have it in MEOH. So at second equivalence point, you know, 100% of this will be reacted, 100% of this will also be reacted, 100% of this will also be finished. Okay, so here you can write equivalence of NaOH plus equivalence of Na2CO3 plus equivalence of NaHCO3 should be equal to equivalence of HCl, right? So this we know already, 0.01 multiplied by 1 plus 0.01 multiplied by 2, 100%, and the n factor is 2, plus NaHCO3 is 0.01 multiplied by 1 should be equal to volume, right? I'll write this as 2 because this is a second equivalence point here. This is 1, right? 2 multiplied by 1. Okay. Then you will get V2 is equal to 0.04 liter, which is 40 milliliter of HCl. So the second case, the titer reading will be 40 milliliter. Okay. Now the third case, from here itself, you can actually find it because first equivalence point was 20, second was 40. First was 20, the second was 40. So what will be this in between one? That will be 20, right? Okay. So you can do it in that way, or else you can calculate as well. No issue. Okay. So third MEOH is used after first EP by HPH. So we found out the first equivalence point with HPH. So then what we are going to find out is how much extra has been used. After we added MEOH, how much did HCl did we add, right? So in that case, NaOH is over, already over, right? It got finished at HPH, already over. Then you have Na2CO3 and NaHCO3. We need to understand, okay, HCl, MeOH. So second EP. So now 50% of this will be, because 50% is already new, we have already accounted for that in the first EP, right? Now 100% of this. Okay. So then we calculate, we will have equivalence of Na2CO3, sorry, Na2CO3 multiplied by 1 by 2 plus equivalence of NaHC3 equal to equivalence of HCl. Correct? So this will be 0.01 multiplied by 2 divided by 2. So plus 0.01 divided by this will be equal to, this will get cut. So you'll get V, can I write? V2 minus V1, basically. It's between that V2 and V1 multiplied by 1. So V2 1, you'll get it as 20 milliliter again. So as I said, logically, you would have found it 40 minus 20. And by this calculation also, you can do it. So I hope double titration is very clear to you, right? So just understand when we are using the two indicators, what do we get at each equivalence point? Then this concept will be easy. Okay, you can practice more questions, PYQs or questions from university or P Bahadur or anything. Okay, thank you.